Okay, so let's move forward. About this slide demonstrate that the arrow function and its complementary arrow function. This is an arrow function we have introduced before, or you have learned before, but this is arrow function, odd arrow function, or some people call it as a complementary arrow function. So this table we are going to give you and to indicate it that at arrow function z, while z at 0, then arrow function of 0 equals to 0. Give you another examples here. While z equals to 0.25, the arrow function of 0.25 is 0.2763. And let's move forward. Then while the z at 2.8, then the arrow function of 2.8 is near 1, is 0.9999. So which that also confirm that as long as the z uh, equals to or larger than 2.8, then the arrow function is near 1. And as we mentioned before, the arrow function, the the maxima value for arrow function is 1. Okay, so it's within like so the property. Oh, sorry, for the property we have shown this before. So the arrow function z, arrow function at infinity is equals to 1, and approach negative infinity is -1. So the value for arrow function is ranging between -1 up to 1. So just for your reference. Okay, so I'm going to give you an example for diffusion couple we just mentioned. The first diffusion couple, this one. Okay, so what we have here is we have a copper, we have a nickel copper diffusion couple, and the interdiffusions happens of copper in nickel, and the temperature uh now is ranging between 200 up to 500. And what we have, what type of diffusion couple we have here is we have a nickel, pure nickel, bind to copper nickel alloy. And the diffusions happens. So, and the question, I mean, this example demonstrate that the diffusivity equals to D0. Here, give you to you times the explanation. Negative activity here divided by kT. So as when you change the increase the temperature, then you can estimate the roughly and the diffusivity into this diffusion couple. And next, uh, for example, like at 400 degrees C, which means that is 676 K, the diffusivity equals to 2.7 times 10 to 15. And under this 400 degrees C or 675 K, then can you plot the concentration of copper as a function of location? Because when you increase the temperature, then for sure the interdiffusions happens. Especially we have higher nickel here, lower nickel here, and instead of that, we also have a higher copper and no coppers at your left-handed side. So if we are interested in on the copper concentration profile as a function of time, then you can just plot this figure. This is a concentration of copper, and this is concentration will be equals to 0.6. So due to this is diffusion couples, and also this is a step function we have learned in prior slides. So you can easily to write down the concentration of copper as a function of time and location. But I hope that you can write something down here. We assume the thickness of this diffusion couple is long enough, allowed the concentration at the right-handed side of this diffusion couple remain constant, and also at this end. Okay, so under these boundary conditions, we have show you before. Actually, is this one. The boundary conditions is at your right-handed side, concentration remain constant, at your left-handed side remain constant as well. Under this situation, you can use this results, just copy this results, right? So here, so you can you take the average for this concentration plus 0 and plus the difference. Use C copper minus this times error function iota. So this is the results. This plus this divided by 2, and this minus this divided by 2 as well, and times error function iota. So this is the results. And if you try to use this, you just insert or input this equations into your origin software origin or Excel. Then you can plot the step function as a function of time and location. At before interdiffusions happen, the concentration profile for copper show like this. But as time increase, so you input the diffusivity, and also you input the time here. You use the 5 days. This is in seconds, so you just simply converted the 5 days into seconds. Then you can plot this concentration profile in green or in gray. Then as time increase up to 25 days, then you can get this profile. So as time increase, we visualize that if you're interested on X at 1 micrometer, then concentration decrease. But if you focus on the X at negative 1 micrometers, you can visualize the copper concentration increase. And most important part is there are 3 characteristic locations does not change. The concentration do not change with time, which is at x equals to 0. The concentration always equals to less plus less. Take the average for less plus less. And also on your right-handed side and left-handed side, the concentration remain constant even as time increase. Okay, so this is regarding to the diffusion couple. So let's move to the second examples here. What we have here is we have the diffusion source, limited diffusion source on the top of our substrate, and also increase the temperature and allow the diffusing atoms limited diffusing atoms diffuse into our substrate. And due to it is limited diffusion source, so the concentration profile, concentration of diffusing atoms decrease as time increase. So that's what we call a limited source case or surface concentration decreased case. But how to plot or get the corresponding solutions, corresponding concentrations of diffusing atoms change with location and time. So, but I just want to remind you, actually, this diffusions patterns belongs to one-dimensional diffusions pattern, which means that you can visualize the concentration change mainly along one directions. We call one-dimensional diffusion case. So, in order to solve or interpret how this concentration profile changes, so we use this as an examples here. So this case will be the non-steady state solutions and belongs to one-dimensional square function. So what we have here is we have nickel, copper nickel, and nickel alloy. So we insert the diffusion source of copper atoms in between pure nickel alloys. So when you try to plot the concentration profile for the copper, then you can have we don't have a copper at your left-handed side, but at the center, we do have a copper. The concentration would be 0.6. Then on your right-handed side, we don't have copper as well. So after you simply draw or plot this concentration profile, you visualize this belongs to square function. Square function, right? Square, the shape like the square, so we call a square function. And this diffusion, when diffusion happens, we believe this copper will diffuse to left-handed side and right-handed side simultaneously at the same time. And the concentration profile change mainly happens along one dimensional, so we call it as a one-dimensional square function. So how to solve how to get the concentration profile, this concentration profile as function of time and location. The first thing come up from your mind is you have learned, you get the solutions for step function. But this similar, right? Because this looks like just half of this, half of or three two-thirds of this materials. It turns like have can be related with, right? So So the solution here is we are going to use a superposition technique，就是堆叠的技术。因为你发觉到就是这个其实跟前面的那个diffusion couple 长得很像，对不对？那我们只是再多了一个 nickel，你可以这样想。但那个叫做 step function，但这个叫 square function，主要是因为我们还有多了一个这 nickel。So we know the corresponding solution for step function. So how about we can if that possible to stake also superposition two-step function to form a one square function. Then I have chance to get a corresponding solution for this. 所以我们可不可以用叠加的方式来得到这个 square function？用什么 step function？因为我们在前面 step function 我们已经知道那个解了嘛。So we use this green line superposition with this blue line superposition with this green line. And for this blue line actually is step function, and this green line also a step function. So let's check whether this two step function can form this one square function. So while x smaller than 0, we got a 0 here and also 0 here. And while x in between 0 and delta x, I have C0 plus 0. So I got C0. So within this, actually the concentration equals to C0. And while x larger than delta x, this region, then we can see that the concentration is C0 plus negative C0. So we got a 0 here. So it turns out that we can use this two step function to form this square function. So so let's double check this, right? If this, you can use the x equals to 0 because you sum this together, you got 0. And at the center region, I got a C0 here, and you use C0 to plus 0 equals to C0. And on your right-hand side, we have C0 plus negative C0, we got 0, and also 0 here. So it turns out I can use these two step functions to form this one square function. So based on this concept, so we can get the corresponding solutions. For blue line or blue step functions, I can write it down, right? For blue step functions, the boundary conditions would be while the x in between negative infinity to 0, then the concentration remains 0. But while x larger than 0, so the concentration becomes to C0. So this is a boundary condition for blue as well. So this is boundary condition, but I can directly write down the corresponding solutions is the average C0 plus 0 times the difference, the average of the difference between C0 and 0. So I got the C0 minus 0, take the divided by 2, then arrow function iota. And the bottom and upper limit for this iota is negative in, oh, sorry, is 0 to iota. Okay. And for the, the green one, I also can easily write down the boundary condition is while the x between 0 to delta x, the concentration equals to 0. Okay? While the x larger than delta x, the concentration becomes to negative C0. And I can use this concept to formulate the corresponding solutions. Use this plus this one divided by 2. And use this minus this one, negative C0 minus 0 divided by 2 and arrow function iota will be the typical corresponding solutions. But just keep in mind here, the bottom and upper limit have changed because it was at x equals to 0, but now it's moved to delta x. So here, I need to shift it back, so I use the iota minus delta iota to correct the correct the upper limit。在这里的话，就是唯一记得，因为这个 step function 跟我们刚刚推导的在 x 等于0这里已经有点不一样，它往右 shift 了 delta x。那在 iota 的世界里面，你就要把它减回来，所以就减 delta iota。Okay, so the solution actually this is one dimensional square function. So you just got the corresponding solution for S1 and S2. So you just simply sum them together. So sum them together. So I just use this one, S1, oh sorry, S1 and S2. So I can delete this one plus minus delete, and I also and the rest of part I can take C0 divided by 2 outside. Then this is iota, right? But they have the same bottom limit, but they have different upper limit. I need to use this to minus this one, right? And this is actually I just take the C0 and this is delete, so you got C0 divided by square root of pi. Then next I need to use this to minus this one, so I can simply write them down together. Okay, so this is you plus this to iota, so this is iota or 0 to some. This actually I just integral 0 to iota, but I need to minus, this is minus, right? Minus the 1 is integral from 0 to, this is also 0. And this is iota negative minus the delta iota. So you use this to minus this term. So the term you left is here. So this actually is negative iota minus delta iota to iota. So this is what we have, the iota minus delta iota to iota. OK，你用这个，因为它的积分，它前面这项就是都已经消掉嘛，所以你把 C0 除以根号牌拿出来之后，那你剩下就是积分项的运算。那它用0到 iota 去减掉0到 iota 减 delta iota，那你剩下这一段就是 iota 减 delta iota 到 iota，所以就 the only thing you got is this term。OK，这里 OK 嘛？那 so so we need to move forward。等一下，这就是一个so this is a corresponding solution for this one-dimensional square function. So we are going to like discuss this corresponding solution for this one-dimensional square function. So I just copy this results. Okay, so let's just I'm going to copy this results here. I directly copy this results, and we need to discuss this results. Okay, so this results actually is for Nick as we draw in prior slide. Actually, is we have a diffusion source in between pure nicons, right? So and this is a C0 divided by square root of pi, and we integral this iota minus delta iota to iota. Actually, the integral the thickness of the diffusion source with delta iota thick. So, and we integral this, we have a less spatial calculation integral terms, right? So if we do have limited diffusion source, which means you can consider delta iota. This is quite thin. Delta and how thick it is, it will be delta iota is much smaller than the whole length or whole thickness, so much smaller than iota. And so under this situation, we can just delete or take this integral operator out. So we just convert, we use a delta iota to substitute, to replace this integral operator. 当你就是当你面对这样子运算的时候，你就发觉说，它这个积分项事实上是积在这个扩散源里面，它的就是扩散原子随着这个厚度的改变量。但如果你假设这个很薄很薄的话，那我们就可以把这个积分的项拿掉，因为它很薄，那浓度都是维持一样的话，那我就可以直接把这个积分项拿掉，用 delta iota 来做取代，对不对？因为当初就是你在小时候学积分的时候，不是直接拿这个 delta iota，是因为你知道在这个小小的片段里面，它的浓度会随距离而改变。但当它很薄很薄，然后它的里面的浓度是固定的时候，你就直接可以把积分这个项拿掉，然后变成 delta iota。OK，那 what's the delta iota? We just recover it back. Actually, delta iota equals to dx divided by square root of 4 dt. So we just put it back. So this is what we have here. So the concentration profile equals to C0, the concentration, times the delta x divided by square root of 4 dt and exponential negative iota square. 这其实是 iota square, 对不对? Okay. And if you take a look on what's a C0 times delta x, we can call it as source strength because you use a concentration and times the distance. Actually, is a source strength. Is similar with this one. The concentration of diffusion source times integral along one directions. So you got the diffusion strength. So this is the finalize the concentration profile for this step function. Also, sorry, square function, or for the corresponding solution for this limited for this diffusion case, which are like we have a diffusion source in between two materials. Okay, so this is we put a one-dimensional case. So I hope you can have more ideas about one-dimensional diffusion case. So if you check your table 5.1 in your textbook, they highlight we do have the one-dimensional diffusion case. And this actually is the corresponding solutions for this one-dimensional diffusion case. This is what we show you here. It's identical with this one, nd divided by square root 4 dt. Okay. Okay. So we do have three typical case belongs to one-dimensional diffusion case. But as I mentioned before I move to next slide, I just want to remind you, one-dimensional diffusion case, which means that the concentration profile majorly changes along one dimension. So can be the point source in one-dimensional, line source in two-dimensional, and plane source in three-dimensional. What this means, actually, I did draw uh, for your reference. The point source diffuse along the nail wire. So the major concentration profile change will be along one dimension. So we call a one-dimensional diffusion case. And the ND here, ND means the diffusion strength, right? Here will be the numbers. And after calculate, you got the concentration will be numbers per length because the unit for this is the length. So what's a two-dimensional? The case we call a light source in two-dimensional. So light source, for example, like you have a light source here and allow it diffusion on the sheet. For example, like carbon, graphene or something like that, narrow sheet or something. So you have a light source. So you try to plot the concentration profile for this light source. You got the concentration change mainly along one dimensional. So this we also call the one-dimensional diffusion case. You have a light diffusion source and diffuse along the two-dimensional matrix, can be the sheet or something. So the unit for this light source will be the numbers of diffusing atoms per length. And after you put this ND inside here, then the concentration profile unit for concentration will be the numbers of diffusing atom per area. And this is the case we call a plane source in three-dimensional matrix. We get the plane diffusion source and diffuse into this three-dimensional matrix. And if you try to plot the concentration profile, is the main difference is along this x-axis, one-dimensional diffusion. So it's also called a one-dimensional diffusion case. For this diffusion source, the ND, the unit will be the numbers of diffusing atoms per area because it's a planar area, so you can call it a divided by area. But after you put this ND inside, then calculation, the concentration you got will be the numbers of diffusing atom per volume. 所以在这里的话很重要，就是 one dimensional diffusion case 主要是看说它的扩散 profile 主要是沿几个方向改变。那如果你简单化的话，其实它蛮容易理解的。你可以看一下这个的话，它前一秒钟会是这样嘛？那它下一秒钟会怎样？对不对？然后接着就会是。它会往两边做扩散，所以它再怎么样，它的扩散就是它的浓度的 profile 主要都是沿着一个方向，所以叫 one-dimensional diffusion case。这个也是，就它一开始的时候也是这样，对不对？然后其实有人会问说，老师这里对它是这样，然后这边也是这样，所以它其实前面跟后面的 diffusion profile 不会有任何改变。都长这样，然后下一秒的时候，它们也会一起改变，所以它沿这个方向，它 diffusion 的 profile 只沿一个方向而改变，然后后面都是一样的，这种都叫做 one-dimensional 的 diffusion case。那因为它的 source 不同，所以造就你后来算出来的浓度的单位就会不一样。那像这个是 point source，所以它的 ND 的就是因为是 point source，所以就是数目。那因为下面这里计算出来它的是距离，所以最后它算出来的会是有几个扩散原子，然后per length。那 light source 的话就会是这种 light source 嘛。那它的话就会是它原来的单位就会是有几个扩散源在这个长度里面，那你再把它放进来之后，你最后就会是 就是面的密度，那这边就会是一样，这边因为它原来是一个平面的，那平面的话就会是平面，你就可以考虑这个平面。所以我是这样记，就是这个只有一个点，然后这是一条线，所以是这个几个，然后这个条线。然后这个的话是你用这个一维去看的话，这就会是几个，然后在这个面积里面，然后再除一个距离就会是体积密度。OK，就for your reference. Okay, so this is one-dimensional diffusion. But your textbook also demonstrate that. How about if another one-dimensional is a three-dimensional case? This is for one-dimensional, so it's easy. If you have two, you have less and less times again. But if you have three, so you got the x, y, and z. So you sum them together. So you also sum the bottom term together. So you got the 1/2 here, and here you got 3/2. So you got this. So sum them together, you got 3/2. And regarding to the source part, you got this times this, 2 times this integral along whole space. So you got nd here. And the exponential inside your term, so you got r squared equals to x squared plus y squared plus z squared. So this is three-dimensional case. But probably you're more interested in what type of condition will belongs to three-dimensional diffusion case. If you got a point source in diffuse into three-dimensional matrix, so you will have the diffusion along x, y, and z, and will be different depending on their diffusivity and what type of point source we have here. So this belongs to three-dimensional. So actually, if you check the corresponding solutions, will be the difference is 3/2. This is 1/2. And the same concept you also can play with is a two-dimensional diffusion. So the point source diffuse into two-dimensional matrix. So if you want to draw that, this is the sheet I have, but now instead of so the diffusion source I have is point source. So this point source can diffuse along x, and also they can along y-axis. So you got two-dimensional. So I can write it down, can be like this. Dun, 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 dun. And the other, this will be like this. So we have two-dimensional one. Okay. Don't forget this profile, the same with this here, and this profile, the same with this here. So we have this, we call this as a two-dimensional diffusion source. And for this light source in three-dimensional is, I also can draw that. This is three-dimensional, right? Now, if I have a line here, oh, it's ugly, but okay, I also can write it down. So this is a line, right? So this line can diffuse along x. If this line is along y-axis, so this line can diffuse along x-axis, and also can diffuse along z-axis. So also call them as a two-dimensional diffusion source. Okay, so this is two-dimensional, and the difference is 2/2. So it's easy to remember. For one dimension is 1/2, and two dimension is 2/2, and three dimension is 3/2. So depending on different diffusion source and matches you have, so you need to determine what type of diffusion, what kind of, what type of is one or two or three dimensional diffusion case you have, then you can write down their corresponding solutions for them. Okay, so let's move forward. Okay, so here is so that's why we need to learn what type of diffusion, which dimensional diffusion case you have. But move back, actually for this one, for the one-dimensional square function you have, I told you you can just superposition two um, step functions, right? But some people also say that, Professor, is that possible to have the other choice for get the square function instead of like I use blue one to minus green one? Yes, so I provide the solution too. You don't want to use minus, you want to use a plus. So you also can decompose this step square function into two uh, step function. Oh, sorry, this is you sum them together, right? And this is minus. So I can use this blue step function to minus this green step function. Then you also can get the same results. But the one is so this is also the same idea. You need to check them, right? So I so let me that is like if x is smaller than 0, so you use this to plus this one, so 0. And this minus this one, you C0 minus 0, you got C0. And C0 minus C0, you got 0. So you can simply get the solutions minus the solutions, then you will get the same results. Nothing different, but the technique you hear is you have two uh, step functions with positive concentration. Because some people use this one, they just confuse. Is that possible? We do have the really, it's impossible to have a concentration, negative concentration case. So it's difficult to understand in for some people. So the other choice probably will be here. So you use like a two-step function. You just use this blue one to minus this green one. So you will get the same results. Okay, so just for your reference. Okay, so we finish. Here we actually for the case, limited diffusion case, we highlight the importance for determining which dimensional diffusion case you have. But we need to put it back because some people probably could will have some questions. The case we just mentioned here, actually, sorry, the case we just mentioned here actually is we have a square function, right? A square function for diffusion source. But the case we discuss here is not that the case. We have just half of that, which means that we have a limited diffusion source on the top of our substrate, not in between two materials. So how to modify the corresponding solutions here? So I will put uh, the I will get all the informations and put everything here. When you try to use when you try to use the um, Excel to like plot the corresponding solution you just get here is the one-dimensional case, then you will get like this. We have the copper nickel alloy in between pure nickels, and I just grab because when the diffusions happens, we know that this belongs to one-dimensional diffusion case because the concentration profile mainly changes along x-axis. So I can write the corresponding solutions down is 1 divided by 2, and nx is the diffusion strength. And in this case, they have give you the activation energy D0, and as long as you know the T is 675 K, then you got the diffusivity for copper. So you got that diffusivity for copper, and you just need to put the time here. Then you can simply plot the concentration profile. And the blue one actually is before diffusions happens, and as time increase to 30 minutes, then you can see the concentration decrease with time increase. But this is the step function we just discussed about, right? But the case actually we call a limited case, right? It's not the case we just discussed here. Actually, is we call an infinite median. So this is solutions we have derived for this infinite median. But the one we just uh, talk about is we have a limited diffusion source deposit on our matrix. It's some kind of half of it, less infinite median. So how to modify the corresponding solutions we have? Don't forget this, if you have diffusion source, the atoms can move left-handed side or right-handed side, right? They can go both sides, but for this case, we call a semi-infinite median. They can only move to right-handed side. But if this two case, we do have the same numbers of diffusion strength, then which means that on your right-handed side, the concentration should be double of left-handed side. So this is the corresponding solution for this semi-infinite median. Okay, just times 2. Then you can get this one. So the button will be slightly changed because we times 2. So we can delete this term. So this is a final result we have for this semi-infinite median. OK, so 在这里的话就要记得，我们刚刚推导的，是为了要方便从step function，然后推到square function，然后它的例子就会是我的 diffusion source 要在中间。但如果是你的，当然你的 case 如果是这个，那就直接用这个解没有问题。但如果你的条件，你的 condition 事实上只有一半，就是一样是 limited source，但只有往逆孔做扩散的话，那就要记得，因为它这个 coupler 没办法自由的往两边做扩散，它只能往一边扩散的时候，它浓度就会是这个的乘以2，所以这个要记得一下，就这边要乘上2，它叫 semi-infinite median。OK， 好，那 so let's move to the last one. Also, diffusion alone one-dimensional, but the difference compared to the third one, we call it unlimited source. Instead of limited diffusion atoms we have, or diffusion source we have, in this case, we provide unlimited diffusion atoms on the top of our materials and allow these diffusing atoms diffuse inside our matrix. So the characteristic for this case is we observe the CS, the concentration of diffusing atoms does not change with time, or they always remain CS as time increase. So you can see like when diffusions happens, we can see at T1, and as time increase, you got blue one. So the CS does not change with time, okay, because we provide unlimited diffusing source. Okay, but in this case, how can we gather its corresponding solutions for this unlimited diffusion source case? We are going to introduce your textbook. Actually, you introduce the Laplace transformation. So beginning, I want to introduce what is just quick remind. I believe you have learned this before, Laplace transformation before. So just quick remind, what's a Laplace transformation? It's just converted the t domain to p domain in your function. So let's give you an example here. We have a function f change with x and t. So after Laplace transformation, just mainly converted the domain from xt to xp. So we don't touch the x domain. We just converted the time domain to p domain, and we use this symbol to represent this function f has been converted to p domain, or we use this to demonstrate that this function f has been Laplace transformed. Okay, so how to really practice or convert it f function to from t domain to p domain? You just times the exponential negative pt an integral along t domain from 0 to infinity, then you will have you have successfully to perform the Laplace transformation on t domain to p domain. So this is a diffusion equation we have here. So if I want to perform the Laplace transformation on this diffusion equation, I need to Laplace transform at your right-handed side and also perform on your left-handed side and also on your right-handed side. So we assume the d is constant, so we take the d outside, and the L means that I'm going to do the Laplace transformation on the left-handed side and also right-handed side. And if you check your mathematics the books, you know that Laplace f prime of t, I will get p f Laplace f of p minus f of 0. So this is the information I should provide to you, or you can check from your textbook before, mathematics textbooks. So I do the same idea. I replace f with a concentration. Okay, so I perform the same idea will be this. So p times c of p. Okay, so p times c of p, and I have used this symbol to represent the Laplace transformation, minus c of 0. C of 0, and this 0 means the p at 0, and also means the t equals to 0. Because this is not a transformation term, right? So this is c of 0, and 0, this 0 is t, means t equals to 0. And on your right-handed side, we assume d equals to constant, just copy here. And I need to perform the Laplace transformation on your right-handed side. But this is x nothing related to with t domain, right? So I just use after Laplace transformation term here, copy here, because this term is nothing related with t, so just copy them. 在这里的话要记得，就是 Laplace transformation 简单来讲就是乘上这个黄色这个 term，再对 t 积分从0到无限大。那它只对所有跟 t domain 有关的，所以你在 Laplace 的过程中，走左边这里可以照着公式把它抄过来。那右边这边因为是 x domain，跟 t 是没有关系的，所以就直接照抄。然后这个浓度这里，因为你已经经过 Laplace transformation，所以要放这个 symbol here. So now I need to solve this diffusion equation here. And as we learned before, we need the help from the boundary conditions. So there are 3 boundary conditions. At any time point, the concentration at x at 0, which means that the concentration at the surface remains to Cs. And the second boundary condition, which means the concentration change at infinity, which means at your right-handed side equals to 0. Okay, and the third one is before diffusions t equals to 0, the concentration at x any1 equals to 0. Before diffusions happens, there's no diffusing atom within your substrate. So I'm going to use these 3 boundary conditions to try to solve the concentration profile after Laplace transformation. And just before we really solve these diffusion equations, I just want to introduce you the step by step, the roughly flow chart for the following deviations. We are going to get the concentration profile after Laplace transformation. Then we are going to use the solutions we find in P domain and convert it back to T domain. This is the solutions we in P domain, then we convert it back in T domain. So this is how we deal with. Okay, so we just copy this one and use this boundary conditions. But as you know, before diffusions happen, the concentration should be equals to 0. So I got a 0 term here. So after, so 0, 10, you only have list 2 terms. And I just move list 10 to right-hand side and divide it by D, so I will get this result. So now it's easy to get the concentration profile by this diffusion equation, I mean differentiation equation, right? You got the solutions in P domain show like this. A1 exponential square root of P divided by D. This X is outside, okay, times X. And you also got the A2 exponential negative square root of P divided by D, and X is outside. So now so the question here would be, what's the A1 and A2? As long as I know A1 and A2, I can get the solutions in P domain. 在这里的话，就是因为你有这个 boundary condition，所以你已经得到了这个等于零，所以这是个标准解嘛，二次偏位，然后有一个这个，然后等于零，所以你就可以直接写出 A1 exponential p3d，然后 x 在 outside，然后一样是负的，这个是负的 A2，然后这个是负的 x。So there are two boundary condition left, and I have two unknown parameters. So I have chance to know A1 and A2 by using these two boundary conditions. So next, I'm going to copy these two boundary conditions here and write down also copy the solutions I just formulate. Okay, so because this is the solutions in P domain, and this is a boundary condition in T domain, so I need to convert the boundary condition in T domain to P domain, then use them. So this is a Laplace transformation on my boundary conditions. So I Laplace for this CS, and as I mentioned, Laplace, which means that you times the exponential negative pt dt integral along t from 0 to infinity. So you will get the CS divided by P. Okay, so this integral. Then x equals to 0. So this is the solution in P domain, right? So when x equals to 0, so I got 0, 0. So this value actually 0 means 1, 1. So A1 plus A2 equals to this. So I got the A1 plus A2. And the second boundary conditions here is at when partial with x. As we know, the Laplace transformation is nothing related with x, right? So I can't directly label this with after Laplace transformation equals to 0. And this you partial with x, and x while x equals to infinity, this equals to 0, which means that the only possibilities when x equals to infinity is impossible and also equals to 0. So A1 should be 0. Otherwise, it's no way to get the 0 for this results, right? So we got A1 equals to 0. Then I have chance. You only have the value for A2. Because when x equals to infinity, this will be quite large. This value times A1 should be equals to 0. The only possibility is A1 equals to 0. So you got this one. So A2 equals to CS divided by P. So you don't have A1, you got A2. So the solutions in P domain should be written as CS divided by P exponential this term. So this is the solutions in P domain. I need this have less tables to convert the solutions in P domain back to T domain. So if we compare, this is similar with this, right? And Q equals to square root of P divided by D. So I just put it back. So and P here, so I take the CS outside. So I got a CS times this arrow function. Okay, so CS art arrow function and our complementary arrow function, you want put it back, so 1 minus arrow function iota. So this is results in T domain, corresponding solutions in T domain. Okay, and this just for your reference, but just compare this to become here. Okay, so this is the corresponding results when there's no diffusing atoms inside this matrix before diffusions happen. So this is a corresponding solution. We got CS and 1 times the 1 minus error function yield. But however, as you learn, if there's some, you have a C0, I mean concentration of diffusing atoms at C0 before diffusions happen. You need to do some modify. So this is the modification. And you just do the same practice to, to change the boundary conditions to C0 instead of 0. So the only difference here is the boundary condition becomes to C0. Here, the only difference is here. So I hope you can practice this. Okay. Okay. So next, I'm going to give you examples to simply end this part. So as a famous example is we call a carbonization of your steel parts. So we have a methane throw into our furnace, and we have a steel part inside with low carbon concentration inside our furnace. So we hope when you try to write down the concentration profile versus the depth and versus time, so you will get that inside this low carbon steel part and below the surface, and we focus on 60% here. Also, sorry, 60 inch in below our surface. You find as time increase, the concentration of copper increase as well. So this is we call carbon gradient in copperized metals. So this is a regular treatment for our steel parts. Okay, so in order to estimate how much time we need to increase the carbon content uh, inside our steel parts. So this is the example here. Consider we are going to have a gas carbonization of steel with 0.18 weight% at 927 degrees C. Could you please calculate the time necessary to increase the carbon content to 0.35 at 0.4 millimeter below the surface of the gill? So the carbon content at the surface to be 1.15 weight%, and that nominal carbon content of a steel gill before carbonization is 0.18 weight%. So before carbonization, we have 0.18 weight% in our parts. But I hope it can increase to 0.35 at zero point 0.4 millimeter below the surface. So sometimes I used to like draw the map here because it's like we use the methane as our diffusing source, and which is unlimited source. So I draw this kind of plot. As I mentioned, they mentioned that the gill actually have a 0.18 weight% inside this gill, and they flow the 1.15 weight% of methane on the surface, and they're interesting in the zero point 0.4 millimeter, the location at zero point 0.4 millimeter below the surface. And I hope the concentration can increase to 0.35, how much time it take. So it's easy to just write down the solutions we just arrive and put every parameters inside. CS is 1.15, CX is 0.35, 1.15, and 0.18. X is 4 millimeter, will be 4 times 10 to negative 4, and square root of 4 dt. So I take the 2 outside. Dt, diffusivity, they tell you the diffusivity is shown like this. and time is the only one unknown parameters you have. So after calculations, you got the error function of z equals to 0.8247. So after checking the tables, I got the 0.8247. 8247 is in between these error functions. So I will put here and x. Because I want to know what's the x, then I can get the t. So let's say easy, right? You just write down A209 equals to 0.89. Also 80, sorry, 95. And this is A427 is related to 1. So you got the A247x. So it's easy to get the x equals to 0.959. This is 0.959, so I can get the t is around 3,397 seconds. Okay, so this is the way how you like use this corresponding solutions to know or estimate how much time you need to increase the carbon content from 0.18 to 0.35. It around like an hours. Take around an hours. Okay. Okay. So this is the examples. Before we end the sections, I'm going to give you, I'm going to introduce the last information as we call the diffusion length. And I believe lots of you have heard the term diffusion length in several places or several sections. But what is the relationship between the concentration indicated by this distance, diffusion length, and the concentration at the original diffusion source? So what's the relationship between them? 就是说，大家常听到 diffusion length，然后大家都会直接用根号负底题来去代表这个 diffusion length，但很少人去认真的去讨论说，在这个 diffusion length 里面，它跟原来的扩散源的浓度之间的关系到底是什么？也就是说，在这个 lambda 的这个距离的时候，它到底是我们估算的这个扩散距长度，到底当下它是扩散源浓度的几倍，跟扩散源的浓度到底有怎么样的关系？然后这个是大家很少比较不知道，大家都会常用根号符底梯来做估算，就像是我们前面在算那个 narrow scale 的克肯多 effect 的时候，我们用根号符底梯来估算他们真正这个 kosher 的 interdiffusion 的这个距离到底是什么，但那个时候也没有提到说，哎，这个距离到底是跟扩散源浓度之间的关系是什么？So the answer here would be depending on different diffusion case we are going to discuss. For diffusion couple, the corresponding solutions can show here. And this is a limited source and non-limited source. I just grab them, just copy the corresponding solutions for them. But this is obviously 1 divided by 2. So this is a one-dimensional diffusion source, diffusion case we are going to talk about. And this is I just grabbed the equation we derive. And the C at lambda, which means the concentration at diffusion length actually is equals to C0 divided by A. And this is times exponential to -1. And this is just the C at diffusion length can be calculated as here. So this is the answers. So by these three results, you can know the concentration at the diffusion length equals to this, which are related with original diffusion, concentration of diffusion source. But here, I'm going to tell you how we get this results. Okay, for the diffusion couple case, the result is C0 divided by A, right? So if you want to get a C0 divided by A, this part should be 1 divided by 4. So 1 minus 3 divided by 4, you will get 1 divided by 4. So this value should roughly around 3 divided by 4. So it will be 0.75. Under these situations, 0.75 is around here. So the inner should be around 0.8. So under this situation, the x equals to 1.6 square root of dt is nearby 2 square root of dt. So you can use a square root of 4 dt to represent lambda. 在这里的话，就是这三个都是当你把 lambda 带进去的时候，它的相对应的浓度。例如说，在 diffusion couple 的话，它就会是原始浓度 C0去除以8。那在这个 limited source 里面，它就会是原始浓度乘上1的负1，然后这个的话就会符合这个。那我们就是来做估算，就是说，如果这边1/2嘛，那如果这边要是1/8的话，这边要是1/4，那1减掉多少会是1/4？这样这边是1/4，就3/4。那如果你去看 error function 的表，要3/3 0.75的话，那里面这个值大概要是0.8。那这里面要是0.8的话，其实就告诉你 lambda 要是多少，lambda 大概要是根号4 dt。其实正确算是1.6乘上根号 dt，那其实大概就是根号4 dt。那我们就想要跟大家说，为什么大家都习惯用 4 dt 根号4 dt 来用这个 diffusion length？那如果是这样的话，是不是？那我们来看一下这个。If you check the limited source one, if you the lambda at lambda, so it will be the x equals to 0, 0. So you got this. Sorry, this is CS, right? So this is x equals to 0. So you got the 1 here. Then x equals to 0. Okay, then you got this is a C, because this is 0, so this is CS, right? And CS times CS, it will be the same, and exponential -1, so this one should be -1. So you got the square root of 40t. 所以如果是答案是这样的话，那你就可以知道说，因为其实当 x 等于0的时候，这个浓度就会是表面浓度嘛。然后它又是表面浓度乘上1的负1，所以就变成说这里面这个值要是负1。那 x 就要是 4 dt， 所以就证明了在4 dt 的这里，就这个 diffusion length 事实上大概就是为什么是4 dt。And for the last one here, 如果 compare these two, this one should be 3 divided by 4. Then that will allow you have this value. And this will be the same, right? 3 divided by 2, so it's 0.75. So you got the same results. So this is to interpret why the lambda, you can use the square root of 4dt to interpret that. And what's this relationship at lambda versus the original concentration will be depending on different diffusion case you are interested in. OK， 然后 just 另外一个补充的部分 for your reference。Actually, the surface concentration case, actually, you can use this. This concentration does not change with time, right? And you can use this to here. This concentration does not change with time as well. So actually, this part you can consider as this part. CS, this is if you use the 1/2 C0, you use 1/2 C0 to substitute here, you will get the same C0 divided by A. Because you also use a C0 here, so C0 is 0, 0. So 1/2 C0 here, you got the A divided by, so 1/C0 divided by A. This part can be seen as this CS can be considered as this because both these locations does not change with time. And in this diffusion case, this concentration is 1/2 CS. and they don't have concentration inside here. So this will be 0, 0, and 1 over 2 CS. So you got 1 over 8 CS, the same. OK，在这里的话，就是另外一个补充的是说，这个点跟这个点其实都是不随时间而改变的，所以这个 C0除以8是蛮可以比拟的。为什么？因为在这个例子里面，如果 C0在左边 diffusion couple 这里，如果我要把这个放到这里来的话，这里是没有 C0的，里面事实上是没有扩散原子的，所以 C0这里就会是0嘛。那这个 CS 就用1/2的这个的 C0，那这边就会是1/8的 C0。没有，这只是给大家补充，因为有人有发现到这件事，我想说那就跟大家说一下为什么会是这样。Okay, so I'll give you a summary for this part. Uh, um, we have a steady state or non-steady state depending on whether we have a time dependent or time independent equations we have. For steady state, which means that solutions, the concentration of diffusing atoms does not change with time. And time varying means that we do have the non-steady state diffusion patterns, which means that allow us to get the concentration uh, of the diffusing atom change with locations and also time. And regarding to some solutions, you can use a superposition technique to get the corresponding solutions. And the thing is like we use superposition two-step functions, then that will allow us to get the square, one-dimensional square function. So this is we use a superposition technique. This is also the samurai superposition technique. So, and this we spend lots of time to show you how to derive the corresponding solutions for these three typical time-dependent diffusion equation, or you can call it the time-dependent solutions. Okay.